Okay, so I've got this one started for us. First thing we want to do is just sort of count all the carbons that are there and figure out what the empirical formula will be. And so in the longest chain, 1, 2, 3, 4, 5, 6, 7, 1 for every zig and zag. I have 7 there, plus 1, 2, 3 more for all the different branches. So this becomes C10. And then if we're going to have this being all single bonded, which we can see here, then this will have to be a maximum saturation, and so we have our general formula we can use of CnH2n plus 2. So we double this, add 2 more, and so we recognize this as C10H22. Now we go back to our longest chain because we have to figure out that one. 1, 2, 3, 4, 5, 6, 7. And so that is going to be hept. Again, we don't have a lot of variety right now. We know they're all single bonded, so it's heptane. But we do have 3 methyl groups that are attached here, and we need the lowest possible numbering strategy that we can get. And so if we start on the left, we get 2, 3, 6. If we start on the other end, we get 2, 5, 6. Okay, 2, 3, 6 is definitely lower than 2, 5, 6. So this becomes 2, 3, 6 dash trimethyl heptane. Okay, one more to go through here, and then we'll get into the cyclic alkanes. 1, 2, 3, 4, 5, 6. Did I get that right? 1, 2, 3, 4, 5, 6. Yeah. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Lots of different 6s here, so this one is going to be your best choice just because it's the straightest and easiest to see. And we have a bunch of branches on this one. 4 branches to deal with, 3 1-carbon branches, and 1 2-carbon branch. Okay, remember on this one here, that's in the main chain, so there's 1, 2 in that branch there. If we count up all of the carbons then, we had 1, 2, 3, 4, 5, 6 in our longest chain, 7, 8, 9, 10, 11 in total. Okay, double that and add 2 more, and so we get H24. We now want to try and name this guy. And so the longest continuous chain was 1, 2, 3, 4, 5, 6. So it is a hex molecule. They were all single bonded, so like everything else, it's been a hexane or it's alkane molecule so far. And now we have to figure out all of those prefixes here. So I think we can see that the lowest numbering strategy is going to happen if we number from the right. Okay, long distance to go before we get to our branches if we go from the left. So we get 2, 2, 3, 3 as our numbering strategy. One, however, of these is an ethyl group. Ethyl comes before methyl alphabetically, so we should number that or rate that one first. And so now I have 3 ethyl. I have a lot of numbers to put in here. 2, 2, 3. And I'm going to have to make myself some room. I have the 2,2,3 dash trimethyl. Ran myself way out of room here. Hexane. Okay, so that's a big, ugly, nasty one just for fun. Okay, there you go. We've done 9 of these so far. I hope it's starting to make some sense on what we do and what the order of operations is. Okay, there'll be some more practice, obviously, that is needed that we'll find in the textbook. Besides, there are also lots of good examples you can look at there if it's still not making the most sense. Let's finish off the topic for alkanes here and get into the cyclic alkanes, or the circular ring structure ones here. Cycloalkanes are another common way of having a longest continuous chain. The only difference here is that it is a closed loop. When your carbons do form a closed loop, known as a cyclic hydrocarbon, all right, if the bonds between all of those carbons are single bonds only, it is known as a cycloalkane. To differentiate these from the straight and branched chain alkanes. We will add a prefix here because the circular function does kind of change it from the straight and branched chain equivalences. And so we will use cyclo to help denote that you are dealing with a closed loop alkane rather than a straight and or branched chain alkane. Further methyl and ethyl and alkyl branches are possible here, but there is a slight change that we see in the general molecular and empirical formula. You'll notice the +2 is gone. Okay, what happens when I take something like this? I'll just do this propane here. And here I have a propane, but now I want to close this into a closed loop. How am I going to do that? Well, right now there's no place to attach the carbons to each other to close this loop. In order to be able to do this, I would have to lose 2 hydrogens so that I can form the triangular closed loop that I might get here. This causes me to lose 2 hydrogens in order to have a cyclic structure. This is why we have a slightly different molecular formula. Now, alkanes and cycloalkanes are the first examples of what we call a homologous series. And the homology here that we're talking about is really just organic compounds that will differ by one methylene group or a CH2. You'll see that pattern here on the table below. Okay, if I take methane, CH4, it only differs from ethane by 1 carbon and 2 hydrogens, which differs from propane by the same amount, which differs from butane by the same amount. Okay, as we get through these other ones in future lessons, you can compare these different homologous series, but you'll just notice that it's a CH2 difference between the various molecules that you've got. So, let's do a couple of examples here. We've got cyclopropane, cyclobutane, and a couple of other ones here. Let's see if we can't draw these things and maybe even come up with, let's say, a couple of different ways to do them. So we'll pick different ways for each one, so we're not doing, like 20 minutes worth of them here. But let's try cyclopropane. All right, we kind of started with that one. So if I have cyclopropane, all right, I need a closed loop of 3 carbons. In the name, cyclopropane, okay, cyclo is closed, prop is 3 carbons, they're all single bonded. This is still saturated, which means I still need a maximum number of bonds, maximum number of hydrogens here. And so each carbon has to have 4 bonds, so I need 2 hydrogens to satisfy this one, 2 hydrogens to satisfy this one, and 2 hydrogens to satisfy that one. And so you can see the C3H6 or the CnH2n empirical formula for our cyclic hydrocarbons. I have another one I'd like you guys to try, and that is cyclobutane. I have a closed loop of single bonded carbons. How many carbons in this closed loop? All right, props to you guys that didn't have to look at that little naming sheet, but but means 4, so I need a closed loop of 4. What shape should I draw for my line angle formula if I want a closed loop of 4? All right. Start here. There's 1, 2, 3, 4, and now I close the loop. So props to you guys for whoever said diamond. Awesome. Yes, a diamond line angle would be perfect for our cyclobutane. Equal bonus points to those of you guys that said square. That would also work. Okay, but remember that each zig and zag or terminus in the line angle formula gives us one of our carbons. So there's 1, 2, 3, 4, and the bond to close the loop. We don't draw our hydrogens here, but we would assume saturation because we see the single bonds. And so there'd be 2 hydrogens for each one. We would end up with C4H8 for our cyclobutane. Okay, I'd like you guys to pause the video and do the remaining 3. Okay? Actually, what I'll do, I'm looking at the time here, I'm going to put that in the next video, and I'll just put these 3 solutions. Here's your homework assignment. Let's see if you get these right by doing them before you take a look at the next video. So read carefully and follow that 3-step cadence.